Today we're going to learn about propagation delay and different types of hazard. So what is propagation delay? Suppose you have an inverter with input A and output B, and there's a change at the input A. The output B won't react at the same time. So the x-axis is time and y-axis is your input. So it won't react at the same time, but it will take little bit of time to react, and then you will see the change at the output B. So this delay is called propagation delay. So let's talk about hazards. There are three types of hazards: static 0, static 1. So in static 0, if there is some input transition, if there's a transition at the input, and for some combination of propagation delay, the expected output should be 0, but due to propagation delay it goes to 1 and then settles back to 0. This is a static 0 hertz hazard. Similarly, for any input transition and combination of propagation delay, the expected output is 1, but it momentarily goes to 0 and then it goes back to 1. This is a static 1 hazard. So for static 0, this was the expected output, the orange one, and the orange one is the expected output for static 1. So suppose the output is supposed to change from 0 to 1, and uh, the output changes 2 to 3 times, something like this. So this is what is called dynamic hazard. So now I'll show you how let's take an example of a static 1 hazard. So let's draw the circuit. This is from the textbook. So suppose this is a circuit which has two AND gates, and which has two AND gates and one OR gate and one NOT gate. The delay of each circuit is, let's say, 5 nanosecond. The output expression would be F is equal to AB bar plus BC and A So if you write this, you will get something like this. If you write this expression, so this would be 1 and this would be 1 implicant. So let's draw the timing diagram for the following circuit. So I'll make this A, B, C, D, E, F. So this would be 5 nanosecond, 10, 15, 20, 25 and 30. So we'll make this, let's make this D and E. So we'll keep A as high and we'll keep C as high. Okay, and B we will change from 1 to 0. So accordingly E will react after, so E is initially high because it's C is high and B is also high. So as soon as E changes, so after the propagation delay of 5 nanosecond, it will go down. Similarly, D will be low initially and after 10 nanoseconds, so 5 and 5, this will go up. Now let's see the final output F. So as you can see, it's the OR gate, so output would be 1 if any of its input are 1. So if D and V is 1, then so it has a propagation delay of 5 nanoseconds. So I'll start from here. So at here, this is 0, this is 1. So output would be 1, the delay of 5 nanosecond. This is 0, this is 1. It will still be 5 nano, output would be 1. This is 0, this is 1. Again, the output would be 1. Now, as you can see, this is 0, this is 0. The output becomes 0. And then, now it's 1, 0. So it becomes 1 again. So this is, the expected output was 1. But we got the 0 because of propagation delay. So this is how we solve the static 1 hazard. This is the timing diagram for static 1 hazard, and this is how we show the static 1 hazard. So how to avoid static 1 hazard? So it happens because there are two adjacent ones that are not in the same loop. Like in this case, this one and this one are not in the same loop. So by adding one more implicant like this and adding AC, this hazard can be avoided. So we need to make add extra gate. This would not be a minimum SOP, but yeah, if you add this, now if you see at this point, even though this is 0, this is 0, but A and C are both 1, so you will get this one, it won't go to 0. So yeah, this is how we avoid static 1 hazard, by adding an extra AND gate called AC for in your expression of F. Suppose you are given a question like this and you need to solve find a hazard free AND OR circuit for it. So how you will solve it is, you will first draw a K map for this. So this will be A, B, C, D. Let's write all the ones. So this is 1, this is 1, this is 1, 1, 1, 1, 1, 1, 1, 1. Now let's circle all the loops that we have. So this will form one loop, this will form one loop, this will form one loop, this will form one loop. Okay, let's write the expression. This is the expression which will have hazard, and then we'll make it hazard free. So this will have, this is BD plus AC bar plus A bar B bar D bar plus A bar C D bar. Now if you want to make it hazard free, you need to add adjacent ones which are not included in the loop. So in this case, this is the one and this is the one. So by adding this, we need to add this. So this is like B bar C bar D bar and A bar B C. Now let's do the B part of this, which is the product of sum or AND circuit. So in this case, let's do the K-map again. This time we will try to remove. So previously this will remove static 1 hazard and this will remove static 0. So let me write this again. This is 0 0 0 1 1 1 1 0 0 0 0 1. So this are the 0 terms from the expression. This is 0, this is 0, this is 0, this is 0 0 0. So let's write down f is equal to all the loops. So this will form one loop. This is, we need to write entire term. This will form one loop and this will form one loop. So this will become A plus B plus D bar, which is this. Then A plus B bar plus C plus D, that's this. Then A bar plus C bar plus D and A bar plus B plus C bar. Now from this we will add one more term which are adjacent zeros this time and which is not included. So this would be this term. which is b plus c bar plus d bar. So we will add this sum to remove a static zero hazard. So that's how you solve yeah, all end circuit. Drawing all end circuit of this is simple. You just need to add this term and the one more odd term for this. Okay, thank you.